Hello and welcome to my channel. Today we're going to be looking at atomic clocks. Now, atomic clocks are one of the most precise instruments that we have. Time is one of the most precise things that man can measure. And before we go specifically into atomic clocks, I would like to talk a little about timekeeping in general and why it's so important to humanity. Now, the thing we have to keep in mind about timekeeping is that time is not a real thing that we can measure by itself. So we rely on certain events to keep track of it. The events that would be perfect for this would be periodic events, things that repeat, that have a constant frequency. Then we can keep track of time by measuring the cycles it goes by. Another thing that we need to keep in mind is that all parties have to agree on when the time counting began, because without that, we wouldn't know how much time has passed by. One of the more ancient devices that was used for timekeeping are, well, sand clocks and sundials. Sundials would measure the rotation of the Earth, and the day-night cycle was something that had been used for centuries to know and keep track of time. One of the more conventional timekeeping devices was the pendulum clock, which was used for many centuries. Now, in a pendulum clock, there's a pendulum that swings under the influence of gravity back and forth. Now, we can think of this as the pendulum being in different gravitational potential states. And by convention, we take half of this swing to be a second. But the issue with this is that due to the various manufacturing defects and the gravitational variations, um, it's each clock does not have an exact second. And another fundamental problem with the pendulum clock is that it has such a low frequency, which means that we can't really measure nanoseconds or something like that. So moving on, let's look at the quartz clock. Now, the quartz clock is a lot better than the mechanical clock just due to the fact that it has such a high frequency. Now, the quartz clock has a crystal, a piezoelectric crystal that basically vibrates at a certain frequency when an electric field is applied across it. Now, since the frequency is so high, it is a lot more accurate, but the issue is that the frequency uh, depends a lot on the manufacturing process. So each of the clocks made are not exactly the same frequency. Now, since all these clocks had such a variation in frequency, scientists started looking for systems that had the same frequency, whether they were found here on Earth or far away in a distant galaxy. And well, their search led them to the atom. Now, an atom oscillates with the same frequency for given two excited states. So if there was a way to lock a resonator with this frequency, we would get a very precise clock. And as a bonus, the frequency of an atomic transition is very, very high. So this would be the reason why atomic clocks have such a great interest for various applications. Now, before I get into the mechanisms of atomic clocks, I thought I'd give you guys some information about the history of atomic clocks. I'm going to go quickly through the next 3 slides or so, so please pause the video if you'd like to go through it in detail. Now, let's get back to the more interesting stuff. So, for the types of atomic clocks, the main ones are basically the cesium atomic clocks, which is what we're going to look into. In those, there are the cesium atoms, which are at different energy levels because of the magnetic fields. And then there's the hydrogen atomic clocks, which are really good for short-term time measurements. And then there's the rubidium atomic clocks, which are easy to make and is basically just rubidium gas in a glass cell. Now, for how atomic clocks actually work. Yeah, I know the diagram on the right looks like something straight out of Star Wars, but we need all of that complex widgets to sync up the atomic transition frequencies with the microwave resonator, which play the role of ticks in our atomic clock. Now there are lasers to control the atoms, there are microwaves for the excitation, and detectors to calibrate and check if we've reached the resonant frequencies, and we're going to discuss them in the subsequent slides. Now, before we excite the atoms and try to measure their frequencies, it is crucial for us to confine them and make them stationary. This is because if they were not stationary, then they would absorb different frequencies than the one that we intended them to because of the Doppler shift. We can achieve this confinement by creating standing waves using two different lasers going in the opposite direction. If we had three such lasers in orthogonal directions, we can create a 3D lattice. Now the atoms would naturally gravitate towards the potential wells and get confined there and slow them down. Now the confined atoms are sent through microwaves where they're excited and are now in a superposition of excited and ground states. The probability amplitude of the excited states is maximum when our microwave cavity is at the resonant frequency. A laser pulse in a detector is used to measure the probability of the excited states once they come out of the resonator again. We'll look at this a lot closer in the following animation. Now this is what the detector would look like. It measures the light that is released from the atoms and measures its intensity. Let's look at one of the atomic clocks more carefully. As shown in the animation, here are the photon detectors, the microwave cavity, and the lasers we discussed earlier. First, a gas of cesium atoms are first pumped into the vacuum chamber. Then, our lasers are used to confine the atoms into a ball. The ball is then pushed upwards towards a microwave cavity, where they're excited using microwaves to achieve a superposition state. The atoms are then made to emit light using a pulse. Now the intensity is then noted. Now we arrange the microwave at a different frequency that is closer to the resonant frequency. And now we notice that the intensity is much higher. Now we go to a different frequency that is way too high and much beyond the resonant frequency. We then note that the intensity has now decreased. Using such repetitive settings of the microwave, we get to the actual resonant frequency. And that is how we get the microwave in sync. Atomic clocks have become very indispensable in our world. The GPS systems that we all rely on a daily basis relies heavily on it. The different satellites have to interact accurately with each other in order for them to pinpoint your accurate location. Uh, Radio frequency telescopes also need to use perfect timings to sync up with each other between the different antennas, which are located all across the world. Deep space probes need precise timings to navigate through space because time delays make instant communication almost impossible. Atomic clocks can also be used to map out the gravitational distribution across the surface of the Earth by measuring the time dilation, thanks to Einstein. In the future, perhaps atomic clocks can be used to sync up supercomputers in different geographical locations so that they can communicate with each other and work simultaneously. Atomic clocks are one of our greatest achievements, and we cannot measure anything else with such great, tremendous accuracy. But nuclear clocks seem to be promising and might be an improvement. Since they are nuclear excitations, they're less likely to be affected by the environment and therefore more accurate. But what makes them unviable is that they require really high energies in the order of X rays to be excited. Thorium 229 looks promising, but we still don't know the exact energy states, and we are still yet to find its resonant frequency. And finding its resonant frequency is like looking for a needle in a haystack. So for now, we're stuck with atomic clocks. We have to settle for just being accurate to 1 second in 200 million years. Not so bad, huh? So I'm going to leave you with that thought. Thank you for listening, and please subscribe.